question at hand concerns the design of a transfer switch in an existing building with a double-ended switchboard, where each end is fed from a separate transformer. The owner wants to back up one end of the main switchboard with a portable generator. The design involves a new 4000 amps transfer switch with a 4000 amp circuit breaker on the normal feed side. This design proposes disconnecting the neutral ground bond in the main switchboard and bonding it at the transfer switch, since this is now considered the first overcurrent protection device and disconnect for the service into the building. A new grounding electrode conductor at the transfer switch will be extended into the building to the grounding bar in the main switchboard. The owner's engineer objects to moving the bond and believes the 4000 amp circuit breaker is unnecessary. Let's delve into the arguments for and against the 4000 amp circuit breaker and neutral ground bond relocation. Arguments in favor of the 4000 amp circuit breaker and neutral ground bond relocation. Firstly, NEC compliance. The National Electrical Code, commonly referred to as NEC, mandates that the neutral and ground conductors must be bonded at the service entrance. In this scenario, moving the bond to the transfer switch effectively establishes a new service entrance. Consequently, an overcurrent protection device such as the 4000 amp circuit breaker is required, aligning with NEC section 250.6. Secondly, equipment protection. The 4000 amp circuit breaker serves a crucial role in safeguarding the transfer switch against short-circuit faults that may originate from either the generator or the normal power feed. This protection is especially vital because the transfer switch now functions as the initial overcurrent protection device within the electrical system. Thirdly, electrical isolation. The transfer switch ensures the generator is isolated from the electrical grid, which is essential for safety and operational integrity. Relocating the neutral ground bond to the transfer switch guarantees that this isolation is effectively maintained. Now, let's consider the arguments against the 4000 amp circuit breaker and neutral ground bond relocation. Firstly, redundancy. The existing double-ended switchboard design already incorporates redundancy in the power supply system. Incorporating a generator backup further enhances this redundancy, potentially diminishing the perceived need for additional protective measures. Secondly, cost. The installation of a 4000 amp circuit breaker and the relocation of the neutral ground bond can incur substantial costs, representing a significant financial consideration for the project. Thirdly, unnecessary circuit protection. The owner's engineer might contend that the existing circuit breakers within the main switchboard offer adequate circuit protection, rendering the additional 4000 amp circuit breaker redundant and unnecessary. Recommendation. Based on the NEC compliance and equipment protection concerns, it is advisable to proceed with the original design plan. Integrating the 4000 amp circuit breaker and relocating the neutral ground bond to the transfer switch ensures adherence to electrical codes and provides optimal protection for the electrical system. Detailed discussion with the owner's engineer is recommended. To engage in a comprehensive discussion with the owner's engineer to address their concerns and provide a clear explanation of the rationale underpinning your design choices. It's important to highlight the advantages associated with the proposed solution, including enhanced safety measures, code compliance, and superior protection for the electrical system. If the engineer maintains their opposition despite these explanations, seeking a second opinion from a qualified electrical engineer or consulting with the local code enforcement authority can provide additional clarity and guidance. Further expanding on the NEC compliance aspect, it is important to consider specific sections of the code that are relevant to the scenario. NEC Article 230 covers service entrances, and it dictates the requirements for overcurrent protection, disconnecting means, and grounding. When the transfer switch is introduced and the neutral ground bond is moved, the installation effectively becomes a new service entrance as far as the code is concerned for the generator feed. Therefore, all the requirements for service entrance must be met at the transfer switch location. The 4000 amp circuit breaker is intended to serve as the service overcurrent protection device, fulfilling the requirements of NEC 230.70. The NEC also provides guidance on sizing the overcurrent protection. The size of the circuit breaker should be based on the ampacity of the conductors it protects, as well as the rating of the transfer switch itself. It is essential to ensure that the circuit breaker is appropriately sized to protect both the conductors and the equipment from overloads and short circuits. Regarding equipment protection, it is important to consider the potential fault currents that the transfer switch may be subjected to. The available fault current from the generator and the utility source should be calculated to ensure that the transfer switch and the circuit breaker have adequate interrupting ratings. If the available fault current exceeds the interrupting rating of the equipment, a failure could occur, potentially resulting in damage to the equipment and posing a safety hazard. The 4000 amp circuit breaker acts as a first line of defense against these fault currents, limiting the amount of current that flows through the transfer switch and protecting it from damage. In terms of electrical isolation, the transfer switch is designed to isolate the generator from the utility grid to prevent backfeed. Backfeed can occur when the generator is supplying power to the building while the utility is also energized, creating a dangerous situation for utility workers and potentially damaging equipment. The neutral ground bond plays a critical role in preventing backfeed by providing a low impedance path for fault currents to flow back to the source. By moving the neutral ground bond to the transfer switch, the generator is effectively isolated from the utility grounding system, ensuring that any fault currents from the generator will flow back to the generator and not back into the utility grid. Concerning the redundancy argument, it is true that the existing double-ended switchboard provides some level of redundancy. However, the addition of a generator backup provides an additional layer of protection against power outages. Even with a redundant power supply, a failure can still occur, leaving the building without power. A generator backup can provide a reliable source of power during these outages, ensuring that critical loads continue to operate. From a cost perspective, the installation of a 4000 amp circuit breaker and the relocation of the neutral ground bond can be a significant expense. However, it is important to weigh the cost against the benefits of increased safety and reliability. The cost of a power outage can be substantial, including lost revenue, damaged equipment, and potential safety hazards. Investing in a robust electrical system with adequate protection can help to minimize the risk of these costly events. Addressing the argument that the existing circuit breakers in the main switchboard provide sufficient circuit protection, while it is true that these circuit breakers protect the individual circuits within the building, they do not provide the same level of protection for the transfer switch itself. The transfer switch is a critical piece of equipment that is responsible for switching between the utility power and the generator power. If the transfer switch fails, the entire building could lose power. The 4000 amp circuit breaker provides dedicated protection for the transfer switch, ensuring that it is protected from overloads and short circuits. When discussing these points with the owner's engineer, it is important to present the information in a clear and concise manner. Provide supporting documentation, such as NEC references and fault current calculations to back up your arguments. Be prepared to answer their questions and address their concerns. It is also important to listen to their perspective and consider their input. They may have valid points that can help to improve the design. If you are unable to reach an agreement with the owner's engineer, seeking a second opinion from a qualified electrical engineer or consulting with the local code enforcement authority can help to resolve the issue. These experts can provide an objective assessment of the design and ensure that it meets all applicable codes and standards. In addition to the technical aspects, it is also important to consider the legal and liability implications of the design. As the engineer of record, you are responsible for ensuring that the design is safe and compliant with all applicable codes and standards. If a failure occurs and someone is injured or property is damaged, you could be held liable. Therefore, it is essential to take all necessary precautions to protect the safety of the building occupants and the integrity of the electrical system. The grounding electrode conductor, or GEC, plays a vital role in ensuring the effectiveness of the grounding system. The GEC connects the grounding system to the earth, providing a path for fault currents to flow back to the source. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. It is important to ensure that the GEC is properly sized and installed to provide an effective grounding path. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. The grounding electrode should be installed in accordance with NEC 250.52. The resistance of the grounding electrode system should be measured to ensure that it is low enough to provide an effective grounding path. NEC 250.53 provides guidance on methods for achieving effective grounding. The equipment grounding conductor, or EG, is another important component of the grounding system. The EGC connects the non-current carrying metal parts of electrical equipment to the grounding system, providing a path for fault currents to flow back to the source. The size of the EGC is determined by the size of the circuit conductors, as specified in NEC 250.122. It is important to ensure that the EGC is properly sized and installed to provide an effective grounding path. The EGC should be installed in the same raceway or cable as the circuit conductors. Bonding is the process of connecting the non-current carrying metal parts of electrical equipment together to create a lower impedance path for fault currents to flow back to the source. Bonding is essential for minimizing the risk of electric shock and fire. NEC 250.92 provides guidance on bonding requirements for service equipment. All metal enclosures, raceways, and equipment should be bonded together to create a continuous grounding path. The bonding connections should be made using approved methods, such as bonding jumpers or bonding lock nuts. Surge protection is another important aspect of electrical system design. Surges are transient overvoltage events that can damage sensitive electronic equipment. Surges can be caused by lightning strikes, utility switching, or other electrical disturbances. Surge protective devices, or SPDs, are designed to protect equipment from surges by diverting the surge current to ground. SPD should be installed at the service entrance and at downstream locations to provide comprehensive surge protection. NEC Article 280 provides guidance on surge protection requirements. Selective coordination is a design technique that ensures that only the overcurrent device closest to a fault will open, minimizing the impact of the fault on the rest of the electrical system. Selective coordination is achieved by carefully selecting the overcurrent devices and their settings to ensure that they are coordinated with each other. NEC 240.12 provides guidance on selective coordination requirements. Arc flash is a dangerous electrical hazard that can occur when a short-circuit fault creates an arc of electrical energy. Arc flash events can cause severe burns, blindness, and even death. Arc flash hazard assessment should be performed to determine the potential arc flash hazards in an electrical system. Arc flash warning labels should be installed on electrical equipment to alert workers to the potential hazards. Personal protective equipment, or PPE, should be worn when working on or near energized electrical equipment to protect workers from arc flash hazards. NFPA 70E provides guidance on electrical safety in the workplace, including arc flash safety. Power quality is a measure of the quality of electrical power supplied to a building or facility. Poor power quality can cause equipment malfunctions, data loss, and other problems. Power quality problems can be caused by a variety of factors, including harmonic distortion, voltage sags, and voltage swells. Power quality monitoring equipment can be used to identify and diagnose power quality problems. Power quality solutions, such as harmonic filters and voltage regulators, can be used to improve power quality. Energy efficiency is the practice of using less energy to perform the same task. Energy-efficient design can save money on energy bills and reduce the environmental impact of electrical systems. Energy-efficient lighting, such as LED lighting, can significantly reduce energy consumption. Energy-efficient motors and drives can also reduce energy consumption. Building automation systems can be used to optimize energy use in buildings. Renewable energy sources such as solar power and wind power can provide a clean and sustainable source of energy. Electrical system design should consider the use of renewable energy sources to reduce reliance on fossil fuels. Load calculations are used to determine the amount of electrical power that a building or facility will require. Load calculations are based on the connected load, which is the total amount of power that all of the electrical equipment in the building or facility is capable of drawing. Those calculations should be performed in accordance with NEC Article 220. Demand factors are used to reduce the connected load to account for the fact that not all of the electrical equipment will be operating at the same time. Diversity factors are used to further reduce the load to account for the fact that not all of the circuits will be loaded to their full capacity at the same time. Voltage drop is the reduction in voltage that occurs along a circuit due to the impedance of the conductors. Excessive voltage drop can cause equipment malfunctions and reduce the efficiency of electrical systems. Voltage drop calculations should be performed to ensure that the voltage at the end of each circuit is within acceptable limits. NEC 210.19 provides guidance on voltage drop requirements for branch circuits. Conduit is a type of raceway that is used to protect electrical conductors. Conduit can be made of metal or plastic. The type of conduit used should be appropriate for the environment in which it is installed. NEC Chapter 3 provides guidance on conduit requirements. Cable is a type of electrical conductor that is typically used for branch circuits and feeders. Cable can be made of copper or aluminum. The type of cable used should be appropriate for the application. NEC Chapter 3 provides guidance on cable requirements. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electric shock. GFCIs work by detecting ground faults, which occur when current flows through an unintended path to ground. When a ground fault is detected, the GFCI trips and interrupts the flow of current. GFCIs are required in certain locations such as bathrooms, kitchens, and outdoor areas. NEC 210.8 provides guidance on GFCI requirements. Arc fault circuit interrupters, or AFCIs, are devices that are designed to protect against fires caused by arc faults. Arc faults are unintentional electrical discharges that can occur in damaged or deteriorated wiring. When an arc fault is detected, the AFCI trips and interrupts the flow of current. AFCIs are required in certain locations such as bedrooms and living rooms. NEC 210.12 provides guidance on AFCI requirements. Electrical drawings are used to document the design of an electrical system. Electrical drawings typically include floor plans, riser diagrams, and panel schedules. Electrical drawings should be prepared in accordance with industry standards. Electrical specifications are used to describe the materials and equipment that are to be used in an electrical system. Electrical specifications should be clear, concise, and complete. Electrical inspections are performed to ensure that electrical installations comply with applicable codes and standards. Electrical inspections are typically performed by local code enforcement authorities. Electrical testing is performed to verify the safety and performance of electrical equipment. Electrical testing typically includes insulation resistance testing, continuity testing, and ground impedance testing. Electrical maintenance is performed to keep the electrical equipment in good working order. Electrical maintenance typically includes cleaning, lubricating, and inspecting electrical equipment. NEC Article 110 covers requirements for electrical installations, including workmanship, identification, and access. It is essential to ensure that all electrical work is performed in a neat and workmanlike manner and that all electrical equipment is properly identified and accessible for maintenance and repair. When considering the specific details of this transfer switch installation, one should evaluate the short circuit current rating of all the components. The available fault current at the transfer switch location from both the utility and the generator sources should be determined. This calculation should consider the impedance of the transformers, conductors, and other components in the system. The transfer switch and the 4000 amp circuit breaker must have a short circuit current rating that is equal to or greater than the available fault current. If the short circuit current rating of the equipment is not sufficient, the equipment could be damaged or destroyed in the event of a fault. Another important consideration is the coordination of the overcurrent protection devices. The 4000 amp circuit breaker should be coordinated with the other overcurrent protection devices in the system to ensure that only the device closest to the fault opens. This coordination can be achieved by selecting circuit breakers with appropriate time current characteristics. A time current characteristic curve shows the amount of time that a circuit breaker will take to trip for a given level of overcurrent. By comparing the time current characteristic curves of different circuit breakers, it is possible to determine whether they are properly coordinated. In addition to the 4000 amps circuit breaker, it may also be necessary to install surge protection devices at the transfer switch location. Surge protection devices can protect sensitive electronic equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, utility switching, or other electrical disturbances. The surge protection devices should be selected based on the voltage and current levels of the electrical system. The location of the transfer switch should also be considered when designing the electrical system. The transfer switch should be located in a dry, well-ventilated area that is accessible for maintenance and repair. The transfer switch should also be protected from physical damage. It may be necessary to install a separate enclosure to protect the transfer switch from the elements. The grounding system should be designed to provide a low impedance path for fault currents to flow back to the source. The grounding system should be installed in accordance with NEC Article 250. The grounding system should be bonded to the building steel and to any metallic piping systems. The size of the grounding conductors should be determined based on the size of the service entrance conductors. The neutral conductor should be bonded to the grounding system at the service entrance. The neutral conductor should not be bonded to the grounding system at any other location. This is to prevent circulating currents from flowing through the grounding system. The generator should be sized to meet the load requirements of the building. The load requirement should be determined by performing a load calculation. The load calculation should consider the connected load, the demand factor, and the diversity factor. The generator should be capable of supplying the load during both normal and emergency conditions. The generator should be equipped with a transfer switch that will automatically transfer the load from the utility power to the generator power in the event of a power outage. The transfer switch should be designed to prevent backfeed of power to the utility grid. The generator should be tested regularly to ensure that it is operating properly. The generator should be maintained in accordance with the manufacturer's recommendations. The electrical system should be inspected regularly to ensure that it is safe and operating properly. The electrical system should be maintained in accordance with NEC Article 110. Any deficiencies that are identified during the inspection should be corrected promptly. Electrical safety is of paramount importance. All electrical work should be performed by qualified electricians. All electrical work should be performed in accordance with applicable codes and standards. Electrical workers should be trained in electrical safety procedures. Electrical workers should wear appropriate personal protective equipment when working on or near energized electrical equipment. Electrical equipment should be de-energized before it is worked on whenever possible. Lockout-tagout procedures should be followed when de-energizing electrical equipment. Electrical workers should be aware of the potential hazards of arc flash and shock. Electrical workers should be trained in arc flash and shock prevention procedures. By carefully considering all of these factors, it is possible to design an electrical system that is safe, reliable, and efficient. It's also important to document all the decisions made during the design process. This documentation should include the load calculations, the short circuit current calculations, the coordination study, and the grounding system design. This documentation will be helpful for future maintenance and repairs.